Click the play button and observe the person performing a bungee jump into the creek from the bridge. During this motion, is there any change in the potential energy and kinetic energy of the person?
So this means when the kinetic energy increase, the potential energy will reduce.
The change in the gravitational potential energy of a person is proportional to the height through which he falls. Similarly, kinetic energy of the person increases as his velocity increases. Let us calculate the kinetic energy and the potential energy at two different points of fall of the person. Click the play button to make him fall to the first position A. Height h1 equal 400 meter. Velocity v1 equal 23 meter per second. Mass m equal 40 kilograms. G equal 9.81 meter per second squared. U equal mgh1, which equal 40 times 9.81 times 400, which equal 1.57 times 10 to the power 5 joule. K equal half mv1 squared, which equal half times 40 times 23 squared, which equal 1.06 times 10 to the power 4 joule.
So this means at the position A, the potential energy is 1.57 times 10 to the power 5 joule. And the kinetic energy at that moment is 1.06 times 10 to the power 4 and 10 to the power 4 joule.
At position A, the total mechanical energy of the person can be calculated as shown. Total mechanical energy, E, equals K plus U, which equals 1.06 times 10 to the power 4 plus 1.57 times 10 to the power 5, which equals 1.68 times 10 to the power 5 joules. Now, click the play button to make him fall to the second. Height h2 equals 300 meter. Velocity v2 equals 50 meter per second. Mass m equals 40 kilogram. G equal 9.81 meter per second squared. U equals mgh2, which equals 40 times 9.81 times 300, which equals 1.18 times 10 to the power 5 joules. K equal half mv2 squared, which equal half times 40 times 50 squared, which equals 5.00 times 10 to the power 4 joules. Height h2 equals 3. At position B, the total mechanical energy of the person can be calculated as shown. Total mechanical energy, E equal K plus U, which equal 5.00 times 10 to the power 4 plus 1.18 times 10 to the power 5, which equal 1.68 times 10 to the power 5 joule. Total mechanical energy, E, of a system is the sum of the kinetic energy, K, and potential energy, U, of the objects within the system. At position A, total mechanical energy equals 1.68 times 10 to the power 5 joules. At position B, total mechanical energy equals 1.68 times 10 to the power 5 joules.
During the conservation of energy, the total mechanical energy at any point, any height, any position will always constant. If there is no loss of the energy due to heat, due to friction, and so on, we assume that the energy, total energy conserved and no energy lost as heat.
What do you infer from this? Answer: the total mechanical energy of a system, E, is always a constant. The principle of conservation of energy states that energy can be converted from one form to another, but it cannot be created or destroyed.
So this is a principle of conservation of energy. Energy cannot be created, but it can be transformed or changed, converted from one form of energy to another form of energy.
Total mechanical energy, E, of a system is the sum of kinetic energy, K, and potential energy, U, of the objects within it. E equals K plus U. The principle of conservation of energy states that energy can be converted from one form to another, but it cannot be created or destroyed. Click the play button to observe the free fall of the ball from a height edge to the ground. Observe that when the ball falls from a height edge, the velocity v of the ball increases. Thereby, the ball gains kinetic energy at the expense of its potential energy. Hence, we see that there is a change in the form of energy. Click the play button to make the ball fall through a distance edge. At this position, the velocity of the ball changes to v. Thus, kinetic energy, K, equal half mv squared. After falling a distance of edge, kinetic energy of the ball, K, equal half mv squared. Derivation. When the ball is released from a height edge, u equals 0. Using v squared equal u squared plus 2as, v squared equals 0 plus 2gh, v squared equal 2gh. Change in kinetic energy equal half mv squared minus 0, which equal half m times 2gh. Therefore, half mv squared equal mgh. Click anywhere between the initial and the final position of the ball to select a height edge.
So that means that no matter how at any position, okay? So at any position, we use 1/2 mv squared equal to mgh. So if the height at any distance shown, so no matter how the velocity when we use the principle of conservation of energy, 1/2 equal to mgh, that is for the conservation. The loss of the potential energy will be equal to the gain of the kinetic energy.
Using half mv squared equals mgh, calculate the velocity at that height and click compare.
Okay, so this one we skip.
Click reset and summary. When the ball falls from a height edge, the velocity of the ball increases, its kinetic energy increases, and its potential energy decreases. Half mv squared equals mgh. Click on the battery-operated car to move it. The car is moved by a resultant force F and is displaced through a distance S. The work done, W, on the car is given by W equal Fs. work energy theorem. Change in kinetic energy of a body is equal to the work done on the body by the resultant force. Before the car is moved by a force F, its initial kinetic energy is expressed as Ki.
Initial kinetic energy.
After the car has moved through a distance by a force F, the final kinetic energy of the car is Kf.
So that means that the change in the kinetic energy will be, or the
Applying
difference.
the work energy theorem, work done W equals Kf minus Ki. Therefore, Kf equals W plus Ki. Taking this car as an example, let us derive an expression for work done in terms of change in kinetic energy. When the car of mass m moves from an initial position Si to a final position Sf with an acceleration a, force F equals ma. A equals dv over dt. F equals m times dv over dt.
A is dv over dt. That means the change of the velocity over the time. So F equal to ma. That means m dv over dt.
Derivation. W equals integration of f ds from limits Si to Sf, which equals integration of m times dv over dt times ds from limits Si to Sf, which equals m times integration of ds over dt times dv from limits vi to vf, where vi is the initial velocity of the car, vf is the final velocity of the car. W equals m times integration of v dv from limits vi to vf.
So this means that the work done also equal to m integration v dv.
W equal m times v squared over 2 within limit vi and vf, which equal half m times vf squared minus vi squared, which equal half mvf squared minus half mvi squared, which equal kf minus ki. Thus, work done on the car is equal to the change in kinetic energy of the car.
So that means that work done will be the change of the kinetic energy of the car from one position to another position.
Let us now calculate the resultant force on the car using the work energy theorem. M is the mass of the car. S is the distance traveled by the car. W is the work done on the car. Vi is the initial velocity of the car. Vf is the final velocity of the car. W equals Kf minus Ki. Fs equals Kf minus Ki. F equals Kf minus Ki over S.
So from here, work done is equal to Fs. So work done is equal to Kf minus Ki. That means at the end, we get that the F is equal to Kf over Ki final kinetic energy minus the initial kinetic energy over the distance.
Drag and drop the values in the appropriate boxes. Calculate the resultant force and click compare.
Okay, so this one, M, just put in the M 0.2. So that means that V final is 1, V initial is 0.5, and S is 2 meters. So what you get, then later you calculate it. So that means that from here, we will get that, okay, 0.2 over 2 times 1 square minus 0.5 square. Okay, so over 2. So we get it 0.0375. So that means that, okay, so I can, okay.
Now enter your own values and click compare to check the results.
Okay, so that means that, okay, you just enter any value so you can check it. So no matter how, okay,
according to work energy theorem, change in kinetic energy of an object is equal to the net work done on the object. W equals Kf minus Ki.
So ladies and gentlemen, these are the work done, work equal to Kf minus Ki by using the change in kinetic energy, by using the work energy theorem. Okay, so ladies and gentlemen, so that is the lesson for today. So now cut chat, dan awak terus live pergi YouTube tu. So dah saya akan ambil sendiri. So typekan nama sendiri. Thank you. Good luck for all. Don't forget to write your name, Okay, Eric.